Hello and welcome to the feedback video for assignment 4, Forces, Torque and Equilibrium. In this video we're going to look at all the questions in the assignment, and at the end of the video you'll be asked to complete a question that includes some similar concepts. Please pause the video, attempt the question and hand it in to your teacher as soon as possible. Okay, so in this first question it's asking you to calculate the torque produced by the weight of the aircraft about the pivot marked X in the diagram. And as torque is the turning effect of a force, and is calculated by multiplying the magnitude of the force by the perpendicular distance between the pivot and where the force is acting, we just need to highlight these values in our diagram. Here we have the weight force, which is also given in the question. Weight is always said to act vertically down from an object's center of mass, and this is what causes the turning effect. And here is the perpendicular distance from the center of mass and the given pivot. Once we've highlighted these variables, we need to select the appropriate equation. You also need to be careful here. The weight is given in kilonewtons, kilo meaning times 10 to the power 3. So the weight is 180 times 10 to the power 3. Once you type these variables into your calculator, you should get an answer of 504,000 Newton meters. And because torque is a vector quantity, we should not only state its magnitude but also direction. In this case, from the diagram, we can see it is in the anti-clockwise direction. Question 2 wants you to define two key terms from the forces and equilibrium subtopic, torque and equilibrium. Torque is the turning effect of a force around a pivot and is measured in Newton meters. From the diagram, you can see that the wrench has a pivot at the nut, and a force is being applied to it. To calculate the magnitude of this turning effect, we multiply the size of the force by the perpendicular distance from the force to the pivot. We can also derive our units from here too, as the SI unit of force is newtons, and the SI unit for distance is meters. As we multiply these values together, the resultant units are Newton meters. As forces are vector quantities, torque is also a vector quantity and must have a direction, usually stated as clockwise or anti-clockwise. And from the equation, you should be able to see that if you want to increase the turning effect of a force, then you must either increase the force applied or increase the perpendicular distance from the pivot. Equilibrium is when an object has zero linear acceleration and zero rotational acceleration. We can define equilibrium by the specific conditions by which it occurs. An object is in equilibrium when both the total external force is zero and the total external torque is zero. Let's look more closely at these conditions for equilibrium. The first is that the total torque within the system is equal to zero, or you could say that the total clockwise torque equals the total anti-clockwise torque. And the second condition is that the total force acting on the system must also be zero, otherwise the system would be experiencing a resultant force and therefore accelerating. When approaching a diagram in equilibrium problems, it's important to draw only the forces acting on the rotating object, in this case the beam of the seesaw. The two masses on either end certainly push downwards on the ends of the seesaw with their weight force, and the pivot provides a support force upwards. However, do not forget that the beam will have a weight too, and if the beam or object is described as uniform, then its weight will act from its center of mass, which is directly in the middle of the object. Now, although it is acting at a distance of zero from the pivot and therefore causes no torque, it is still important, as you'll see later. If this diagram showed a seesaw in equilibrium, it would mean that the turning effect of force 1, torque 1, would be equal and opposite in direction to the turning effect of force 3, torque 3. And the total upward support force would be equal and again opposite in direction to the 3 downwards weight forces. Question 3 asks you to calculate the engine thrust, but first we must calculate the lift fan thrust when the plane is in equilibrium. Firstly, I have listed the variables I know, and from the first question, we know the weight force, and we have already calculated the torque due to the weight around the pivot at x. From the diagram, we can see that the force of the lift fan is at a perpendicular distance from the pivot of 7.4 meters. I have just added the two given distances. And it is this alone that produces the total clockwise torque, as the engine thrust acts at the pivot, so produces no torque as its perpendicular distance is 0, and any force times 0 will give a torque or turning effect of 0. Now we must think back to the definition of equilibrium. There must be no resultant torque on the system, and therefore the total clockwise torque must equal the total anticlockwise torque. As we have already calculated the total anticlockwise torque produced by the weight, and we know the distance at which a force from the lift fan acts to produce an equal, an opposite, or clockwise torque, we can calculate this force. After rearranging the expression we had for each torque being equal, we can calculate the force of the lift fan, which creates enough clockwise torque or turning effect to cancel out the anticlockwise torque caused by the weight around pivot x. You should be able to calculate a force from the lift fan of 68,108 newtons, and that is acting in the upwards direction. Okay, so the last part is to calculate the upward force of the plane's engine that is required to maintain equilibrium. Another condition of equilibrium is that there is no resultant force acting on the system. If there was, then the plane would be accelerating in the same direction as that resultant force. In this case, we total up all the upward forces and add them to the total downwards forces. There is only one downward force, weight of the plane, which is 180,000 newtons, and we also know the upward force from the lift fan, which is 68,108 newtons. Forces are vector quantities, just like displacement, velocity, and acceleration, and in equations, directions must be considered. Let's take forces acting downwards as negative and upwards as positive. Weight is acting downwards, and therefore it becomes negative 180,000 newtons in my equation. And if you place the values into your calculator correctly, you should get a value of 111,892 newtons. This is the missing force on the diagram of the plane's engine, and it's positive, which means it's acting upwards. The final question is checking your understanding of Newton's second law and your use of F resultant equals mass times acceleration. The question wants you to calculate the plane's horizontal acceleration. If the plane is accelerating in the horizontal direction, then there must also be a resultant force in that direction. Firstly, I have highlighted the variables given within the question. We have a situation where two forces are acting in opposite directions. Thrust is a forward force, and drag acts against the motion, and is therefore in the opposite direction. We must calculate the resultant of these two forces, as this will be causing the acceleration. This can be found by adding the vectors together. Forces require a direction. I will make all forces to the right positive, that's the thrust, and those to the left negative, that's the drag. This should give me the resultant force, which is calculated to be 130,000 newtons. To calculate the acceleration, I must first rearrange Newton's famous equation F equals ma, remembering that the F in this equation is the resultant force. This gives us a problem. We must also know the plane's mass in kilograms. In the initial part of the question, it gave us the plane's weight, and as weight is calculated by multiplying the mass by the force of gravity per kilogram, which is 9.8 newtons per kilogram, this allows us, after a rearrangement, to calculate a mass for the plane of 18,367 kilograms. After another rearrangement, substituting this value into our equation for acceleration allows us to calculate an acceleration of 7.1 meters per second to the right, or in the direction of thrust. Right, so if you could pause the video, attempt the question, and hand this back into your teacher as soon as possible.